Good afternoon, class. Today we are going to look at inverse functions, and I'll tell you right now it's a little less painful than some of that zeros of polynomial stuff. So first of all, let's see, let me do that, let me do this. First of all, I want to remind you that with a function, we said that there could be no repeated x value. Every x can be assigned to one and only one y value. Now there's a special type of function that we're going to be looking at today called a one-to-one function. That's a function with no repeated y value. It's exactly what you would expect from the phrase one-to-one. For every x, there's one and only one y, and for every y, there's one and only one x. So I'll say a function with no repeated y values. And let's see, I want to look at a graph. We graph quadratic functions in several assignments. So we know a quadratic function is a smooth U shape called a parabola, something like that. Remember, to determine if a graph represents a function, we have the vertical line test. So for a function, if you're trying to decide, is a graph representing a function, you use the vertical line test. Now, and we can see with a quadratic function, I'll just label it ax squared plus bx plus c. We can see that it would clearly pass the vertical line test. No matter where you draw that vertical line, it's not going to hit the graph twice. Now, what about being one-to-one? Do we have any repeated y values on this graph? Look at this point and this one. For this ordered pair, you go to the right, so the x-coordinate is positive, but what's the y-coordinate? For this point right here, sitting on the x-axis, what would that y-coordinate be? 0, is that what you said? What about this one? This point, you'd go left, so the x-coordinate's negative, but what's the y-coordinate for this second point? Another 0. Look at that. We have repeated y values. So this graph is not one-to-one. To determine if a function is one-to-one, we have another test. If you can draw a horizontal line so that it hits the graph in two spots, then that graph is representing a one-to-one function. There, you draw it right there, it hit it twice, so not one-to-one. So to determine if a graph is one-to-one, you need to use the horizontal line test. If you can draw a horizontal line so that it hits it twice, the graph is not one-to-one. Use the vertical line test to determine if the graph is a function, horizontal line test to test for one-to-oneness. Any questions up to this point? Let's see. Looking at number 1. Some of these are pretty fast, these questions here. Is this function one-to-one? This is number 1, and it's a slanted line. I'm not going to bother drawing the picture, but it's a slanted line. As we look at this slanted line, it's certainly, let me blow it up. Let's see there. It's certainly a function. It passes the vertical line test. What about a 1-to-1? Would this thing be 1-to-1? Can you draw a horizontal line so that it hits it twice? Where would the horizontal line hit it twice? No, it wouldn't. So it is. That's one of those strange things. It's that negativity. The horizontal line test says whether something's not 1-to-1. If it hits it twice, it's not 1-to-1. Here, no matter where you draw that horizontal line, it's going to be, it'll only hit it one time. And so, for any slanted line, it's always 1-to-1. It doesn't matter what the slanted line looks like. It could have been falling from left to right. You're not going to draw a line, a horizontal line, that will hit it twice. So the answer for number 1, yes, it is 1-to-1. And that's true for any slanted line. What about this one? Oh, I remember I had a class that was insistent, oh, it's about to turn around and start going back here. No, that's not what's happening. If it were going to turn around and start going back, it would have shown that. What it's doing is it's decreasing. It's as you move out here, it's falling from right to left, and it just continues to go down more and more. Can you draw a horizontal line so that it hits it twice? What do you think? Can you draw? I'm going to draw this picture. I think we need to look at it. Hold on. Let's see. This is number 2. And let me make sure I got this. It's going through the origin. It's going up slowly. It's going down slowly. Continues going down. Let's look at my picture. It is continuing to decrease very slowly. It is not going to turn around. If it were going to turn around, they would have had to show that in the picture. Can a horizontal line hit it twice? No, so this thing is 1-to-1. Oh, and by the way, here's a shorthand notation for 1-to-1. 1-1. It is 1-to-1, and that is, so once again, it is a yes answer. And before we go on, hold on. I want to make a general statement for quadratic functions, whether it's opening upward or, let's suppose it's opening downward. Any quadratic function, y equals ax squared plus bx plus c. Any quadratic function, even if one's opening downward, is it 1-to-1? No, you can draw a horizontal line to hit it, so ax squared plus bx plus c, any quadratic function is not 1-to-1. Slanted lines are always 1-to-1, but quadratic functions are not 1-to-1. My brother's always saying, if someone comes up to you and wants to talk math after class today, you tell them that slanted lines are always 1-to-1. However, quadratic functions are never 1-to-1. If you want to say something mathematically to them, I find talking math to strangers or people that I don't want to talk to always gets rid of them, okay? So, next. You know something? We said that a 1-to-1 function has no repeated y values. We've represented functions 3 different ways this semester. With ordered pairs, Well, if it's ordered pairs, it's easy to decide if it's one-to-one. Just look at the y values. Do you have y values being repeated? If so, it's not one-to-one. So let's see. I'll say, first of all, the ordered pair, let me move it down, with ordered pairs, how do you decide if they're one-to-one? Make sure there's no repeated y values. To be one-to-one, there must be no repeated y values. Every y value has to be different, just like every x value has to be different. Now, if you're looking at a graph, it's easy to determine whether it's representing a one-to-one function. Just use the horizontal line test. Seems sort of bright in this room. Did I lower the lights in this room? I don't think I did. I lowered them over there. I think I need to lower them over here. Ah, there went my... Is that better for y'all? I know it's better for me. There. Now, for equations. So, suppose you're looking at an equation. F of x equals ax squared plus bx plus c or something like that. For equations, to determine if the expression is one-to-one, what makes us have these repeated y values? What is it about, thinking about a parabola, why would you have those repeated y values? You're plugging in x values and you're getting the same thing for y. Well, what's causing that? I'm going to go back to what I've said for the longest. Those even exponents, those are the problems, because even exponents take things that are negative and change them so they're positive. That's when you start picking up repeated y values. For something just a little simple equation, y equals x squared, should be enough to convince you. It doesn't matter whether you plug in positive 3 or negative 3. If you plug in positive or negative 3, what are you going to get for y? Whether it's positive or negative, when you square it, what sort of a number are you going to get? A positive number. That's one of the things you've got to avoid. If you're looking at an equation and you're wondering, is that one-to-one? Well, it's probably not one-to-one. If not one-to-one, if the equation has even exponents, like x squared, x to the fourth, what have you, x squared or x to the fourth. I can think of two major things that would make a function not be one-to-one. Even exponents is one of them. I recall our first homework assignment where we were using those graphing tools, the MyLab graphing tools. Do you remember those absolute value functions? What do they look like? We had a little graphing tool for them. Weren't they V-shaped figures? And I made the point that a V-shaped figure has a sharp point. It's not, as opposed to a U-shape. A parabola is a U-shape, but an absolute value is a V-shaped figure. Would that thing be one-to-one? It doesn't matter whether the stuff inside the absolute value bars are positive or negative. Once you take the absolute value, it's going to become positive. So that's another thing. If you have an equation with absolute values, it's not one-to-one. Any questions so far? You may not see where we're going with all of this, but I'm about to get started with it. The inverse of a function is the set of ordered pairs you get when you reverse the x and y coordinates. So an inverse I'll put it like this. It swaps x and y. I'll swap the x and y coordinates. I have two functions I want us to look at here. The first one I'll call f. Let's see. It has the ordered pairs 0, 3, 1, 4, and 9, 5. To form the inverse, all you do is just swap the ordered pairs. So 0, 3 becomes 3, 0. Algebraically, to denote the inverse of f, what we do is we put a little superscript of -1. That's not saying f to the -1 power. That's not saying the reciprocal of f. Raising a function to a power is meaningless. If you see a little superscript of -1 after a function, that means you're reversing the ordered pairs. The inverse of f would be 0, 3 becomes 3, 0. 1, 4 becomes 4, 1. 9, 5 becomes 5, 9. Here's another one. Let's say G. G contains the ordered pairs 0, 0, 2, 4, -2, 4, and 3, 9. What would G inverse be? Which ordered pairs would be in G inverse? Well, the first one wouldn't be very interesting. Reversing 0, 0, you still have 0, 0. 2, 4, what's that going to become when you reverse it? 4, 2, okay. What about -2, 4? What's that going to become? 4, -2, and 3, 9 becomes 9, 3. Comparing these two functions, look at f. I think you'll agree that f is 1 to 1. There's no repeated x values, so it's a function. There's no repeated y values. The original function that I made up here is 1 to 1. What about the inverse for f? Is that a function? When you reverse the ordered pairs, 3, 4, 5, those are different numbers, so it's a function. So when f was 1 to 1, the inverse is a 1 to 1 function as well. I'll just say is a function. Look at G. Is G 1 to 1? 1 to 1 means there's no repeated y's. It is not 1 to 1. The y value 4 is being repeated there and there. That's fine. G is still a function. You can have repeated y values, but when you form the inverse, what happens? The repeated y becomes a repeated x. The repeated y's, when you reverse it, become repeated x values, so we would have to say that G inverse is not a function. So the whole point of this, only 1-to-1 functions have inverses that are functions. That's what I'm trying to say. If the function is at 1-to-1, that means there's repeated y's, and when you swap the y, it becomes a repeated x. So only 1-to-1 functions have inverses that are functions. You can still find the inverse, it's just not going to be a function. And I'll say only 1-to-1 functions have inverses that are functions? Only one-to-one functions have inverses that are functions. Let's look at number 3. Okay. Decide whether the given functions are inverses. So this is a pretty quick one. Can y'all see that? Is this print big enough? Let's see if I can make it a little bigger. Oh, there, that's a little bit bigger. Remember, an inverse swaps the x's and y's. -3, -4, yeah, that looks good. It became -4, -3. 1, 1 stayed 1, 1. What about -6, -7? Is that okay? It became -7, -6, I agree. What about 4, 2? Yeah, it became 2, 4. So are they inverses? What are we going to say? Yes. Okay, are these functions inverses? Well, a cursory glance, -3, -5 became -5, -3. That looks okay. What about 2, 4? What did it become? 4, 2, that's okay. What about 4, -3? It became -3, 4. What about this last ordered pair? What do y'all think? Are they inverses or not? Or are they not inverse? Yes, they are inverses. Okay, just reverse the ordered pairs. Surely there'll be something that isn't. Oh, by the way, if you're finding inverses, we're only concerned about inverses that are functions. Something like this G here that wasn't 1-to-1. And then the inverse was not a function. They don't. If it's not 1-to-1, they don't want you to find the inverse. They only want the inverse if it's a function. So looking at number 5, if it's 1-to-1, find its inverse. If it's not 1-to-1, say not 1-to-1. We better check and see, is this thing 1-to-1? -7, 17. And -13. Look at those y values. Is the function 1-to-1? 1-to-1 means no repeated y values. Is this function 1-to-1? Yes. So let's find the inverse. 19, -7. That should become -7, 19. So it's either A or C. What about 10, 17? What does that become? 17, 10? I think it's got to be C. -10, -13. Reverse the X and Y. I think it's response C. Any questions there? Okay, I think I'll write this one down. Give me a moment to write the problem down. We used to have a colleague. She could do this stuff. She would just talk through the class. She had a document camera, and it was amazing to watch her. The way she could just see the work that she was doing up in her head. And honestly, the students didn't like it because they'd lose track of what she was calling out as she was working it out in her head. So. But still, I just feel like I need to write something down every now and then. Although we could have done this one without writing anything. The question is it 1-to-1? If it's 1-to-1, find the inverse. If it's not 1-to-1, we have to select not 1-to-1. What are we going to choose here as our answer? Is this 1-to-1? No, what's wrong? Okay, that repeated 9 here and here. So not 1-to-1. The first questions here in this assignment, they're pretty fast, okay? So, not 1 to 1. Maybe that's what's shocking y'all, that answers, you get the answers so quickly. But we'll get to some longer problems in a moment. Now, same question on number 7. Is it 1 to 1? What do y'all think? No. Look closely. I think it is. That's a -9 and a +9, a -1 and a +5. All the y coordinates are different. That's what you want. For it to be 1 to 1, the y coordinates have to be different. So it's not going to be response D. It is 1 to 1. Which one? A, B, or C? A, B, or C? B? I agree. Y'all are mighty quiet today. -6, -9 became -9, -6. 18, 9 became 9, 18. -3, -1, just reverse them, -1, -3, and 7, 5 became 5, 7. Yeah, I agree with B. Now, I want to write down this problem and use it as an example. Let me write down, I'm writing down those ordered pairs. Okay. I want you to consider this function that we have. Recall that the domain is the set of all x values and the range is the set of all y values. So with that in mind, well, before that, let's find the, before we start writing out the domain, let's find f inverse. We said that every y coordinate's different. Every x coordinate is different also, or would it be a function? Let's write out that inverse. The -6, -9 became -9, -6. I'm going somewhere with this. If you're wondering what's the point of all of this, I am going somewhere with it. And that became a -1, -3, and that last ordered pair becomes 5, 7, I agree. And now I want to think of the domain. If I wanted you to tell me which numbers are in the domain of f, what numbers would be in the domain of f? The domain is the set of all x values. We're looking at the original function f. Which numbers are in the domain? -6, what else? 18, -3, and 7. I agree. Suppose I asked you for the range of f. Which numbers are in the range of f? -9 and +9, -1 and 5. Notice if a function is 1 to 1, for every x there's one and only one y, and for every y there's one and only one x. Notice there are 4 domain values. There have to be 4 range values. There's a 1 to 1 correspondence. The y's cannot be repeated. Okay, so we took care of f. Now I want to look at f inverse. What's the domain of f inverse? Which numbers are in the domain of f inverse? Which numbers are in the domain of f inverse? Call them out for me. -9, what else? 9, -1, and 5. Well, look at that. The range of f is the domain of f inverse. That shouldn't be a surprise because of the way we're reversing those ordered pairs. The things that started off as y's originally become x's in the new function. The original y values, the range of f, became x values in the inverse. Now, what's the range of f inverse? Which numbers are in the range of f inverse? -6, 18, I agree, -3, and so what have we just now shown? The range of f inverse is actually the domain of the original function f. Do y'all follow our logic here? Or do you follow my logic? The x's in the original become y's in the new function. The y's in the original become x's in the new function. Any questions there? Hopefully that should be obvious, the way the y's and x's are being swapped. So with that in mind, number 8, the domain of f is equal to the blank of f inverse, and the range of f is equal to the blank of f inverse. The domain of f is equal to the range of f inverse, and the range of f, the original y values, are equal to the, you tell me, domain of f inverse. And that's a direct result of the way that we're reversing those x's and y. Okay, next question. If a function has an inverse and f of -3 is equal to 6, then f inverse of 6 is equal to, so hold on, let me write this down. This is number 9. F of -3 is equal to 6, so f inverse of 6 is equal to, let me make sure I wrote it down all right. Okay, there. Okay, let's just look at this original notation here for dealing with the original function f. The number inside the parentheses is x. So how would you write that as an ordered pair? The number in the parentheses is x. So when x is -3, the y value is 6. Let's find the inverse. The inverse, -3, 6 would become what ordered pair? 6, -3. So look at this question here. Remember the thing inside the parentheses is x. When x is 6, what's the y value? -3. Okay. The inverse is doing nothing more than just reversing the x and y. The thing that was the x became the y. The thing that was the y in the original function became the x. So, coming over here, we get a -3. Oh, and they're going to say some more stuff. Let's see. Okay, before we go on, I need to write some now. I'm going to formally define inverse. Keep in mind, we know intuitively what an inverse is. It reverses all of the ordered pairs. The x's become y's and the y's become x's. But here's an algebraic definition of inverse. The algebraic definition of inverse. Let's assume you have two one-to-one functions. Let's assume f and g are inverses. F and g are inverses. Let's assume they are one-to-one. I'm sorry about that. Mark out that inverses. Assume f and g are one-to-one. F and g are inverses if each of the following is true. There are two conditions. One, if you find f composed with g of x, it has to reduce to x for every x in the domain of g. And if you reverse the composition, if you find g composed with f of x, g composed with f of x reduces to x for every x in the domain of f. I recall some problems 1 week ago when we were looking at composition of functions, and we went through and we found the compositions, and in those problems, everything except for x canceled out. And I said they're trying to get you ready for the definition of inverse. That's what this thing is stating here. If you can find, if you have two functions and you're wondering, now this is true for algebraic functions, the algebraic equations are really what we're thinking of here. If it's an ordered pair, you can look and tell if they're inverses or not. But suppose they're equations. If you find their compositions and they reduce to x in both directions, we say the functions are inverses. If not, then they're not inverses. These things are saying if you start somewhere with an x value and you perform the two functions consecutively, you're going to end up where you start. For example, let's suppose we have the function f. It's going to take 1 to 3 and 2 to 4. And hopefully you'll agree that's 1 to 1. The y values are not being repeated. The inverse would go in the opposite direction. It would take 4 back to 2 and 3 back to 1. Now, those are obviously inverses. What this definition is saying, if you start anywhere you want, perform the two functions, you'll always end up where you started. If they're really inverses, let's see. Let's start at 4. 4 goes to 2, and then 2 goes back to 4. So as we started at 1, 1 goes to 3, 3 goes back to 1. If they're inverses, you will always end up where you started. Well, suppose we consider this function. Let's suppose f takes 1 to 4 and 2 to 3. That's f. Well, if it were going to be inverses, 4 would have to go back to 1 and 3 would have to go back to 2. Let's suppose instead 4 goes back to 2. This is g, and 3 goes back to 1. If you start anywhere in this diagram and perform the two functions, are you going to end up where you started? If you start at 2, 2 goes to 3. Does 3 go back to 2? No, 3 takes you to 1. Not inverses. That definition is saying that if you perform the two functions consecutively, you will always end up where you started. And the only way that's going to happen is if the ordered pairs are just reversed. Any questions there? Well, let's see. I bet you they've given us some functions, and they want us to decide if they're inverses. Let's look at number 10. They've given us two functions, and they want us to decide if they're inverses. Well, if you have two algebraic functions, you want to know if they're inverses, find their composition. If everything cancels out except for x, then great, they're in both directions, then they are inverses. If not everything cancels out, if you're left with something other than x, then they're not inverses. So this is number 10. We have f of x equals 9 over x minus 7, and g of x is equal to 9 over x plus the integer 7. Let me make sure. Yes, okay. Well, I know one thing. Both of these functions are 1 to 1. I'm looking there. I can tell. I can convince myself, yeah, there's not going to be any repeated y values. And you say, well, how did I know that? It's the statement I wrote over here. Where was it? Let's see. Here it is. Equations. They're not going to be 1 to 1 if the equation has even exponents, absolute values. There are other conditions, but these are the most common situations that we're going to see in our in this college level algebra course. Even exponents would make it not be 1 to 1 because those even exponents take negatives and change them to positives, and absolute values for the same reason. Do you see any even exponents or absolute values? Say no. So we can convince ourselves, yeah, these are 1 to 1 functions. But we have to decide, are they inverses? So we're going to have to find f composed with the g of x. That'll be the first one. F composed with the g of x. Recall composition from 1 week ago. F composed with the g of x. That says take g of x and plug it in to f. This is going to get messy, I'll tell you that right now. We're going to take g of x and plug it in over here where there's an x. So we have a 9 over, in place of that x, we have that green stuff, 9 over x plus 7. 9 over x plus 7. And what else do we have stuck down there in the denominator? We replace that x with 9 over x plus 7. We have that minus 7 stuck on there too from the original function f of x. Any questions with what we've done there? Well, if they're inverses, everything except for x has to cancel out. I think two things are about to disappear. What are they? Okay, so the 7s are gone. We have 9 over, that green 9 over x. This is called a fraction that contains additional fractions is called a compound fraction. We're looking at a compound fraction here. I can think of two general ways of reducing a compound fraction. The method that I'm going to use is to multiply above and below by what we call the minor denominator. Here's the major fraction bar. The minor fraction bar is the subsequent fractions that you see within the major fraction. So that 9 over x. The minor denominator is x. We know we can multiply above and below by anything we want to in a fraction except for 0 and maintain equality. Let's multiply above and below by x. What's about to happen down here in that denominator? The x's cancel. So we have 9x on top, and what have we got on bottom?
9.
Just that 9. And what can we cancel here? Remember, if they're inverses, everything has to cancel out except for x. So the 9's cancel. Great. We're halfway through. I'm thinking they probably are inverses. The first direction, it reduced to x. I'm thinking the next direction, if I were going to guess, I would bet, yes, it's going to. But it's not that hard to rig two functions where one direction it reduces to x, but not the other direction. So let's go the other direction now. And this is so messy here, I'm going to recopy my f and g. So f is 9 over x minus 7. And g, I'm just recopying those functions they gave us. It's a 9 over x and a plus 7. We found f composed with g. Now let's find g composed with f. Or as my brother would call it, fog and golf. Let's see. So, g composed with f. We take the f of x and we plug it into g. So we're taking f of x and we're plugging it into g, wherever you see a variable. So we have a 9 over, we've replaced that x with 9 over x minus 7. And we still have a plus 7, that green plus 7, stuck on the side. Any questions on my logic there? Well, we have another compound fraction. What's the minor denominator in this case? X minus 7, let's multiply above and below by x minus 7. We'll multiply here by x minus 7. We'll multiply down here by x minus 7. What's about to happen down here in the denominator? Something's going to cancel out down here in the major fraction. Something's going to cancel out. What's going to cancel out? The x minus 7 right there. So we have a 9. We have a 9 times the purple x minus 7. And what have we got left over in that denominator there? We still have something down there. That 9. And we still have something else. What else do we have that I have to write down? That green plus 7. Do not decide to distribute the 9 through. That'll just give you more work. Remember, we're trying to cancel. We want everything to cancel out except for what? X. So let's get started. I see something canceling real fast. These 9's cancel out. So we then have, there's nothing to distribute, so that, I guess we have a 1 times x minus 7. That's just an x minus 7. And we still have that plus 7. Look at this. What else is about to disappear? The 7's leaving us with just x. Both compositions reduce to x. So what do we conclude? Are these functions inverses? Yes. F and g are inverses. If someone gives you two arbitrary functions and asks you, are they inverses? You can find their compositions. If everything except for x cancels out in both directions, then great, they're inverses. Now, if even one y doesn't cancel out, if you're left with anything other than x and f composed with g, the first one, you can stop. You know that they're not inverses. But if they're inverses, their compositions should reduce to x in both directions. Any questions here? So I guess the natural question is, we said yes, they're inverses. You give me two functions, I can tell you if they're inverses. So the natural question is, okay, suppose you have a function, how do you find its inverse? Any questions? Oh, I better type in I better go back before I get timed out. Are they inverses or are they not inverses? Yes, they are inverses. Any questions there? All that work just to select, yes, they are inverses. Okay. I need to write some stuff first. Okay. How do we find the inverse of a one-to-one function? I'll say, how do we find the inverse of a function? We have a little procedure here, but it's a short procedure. It's not like the cut point method or completing the square with all those steps. First thing you have to do, you have to verify that the function they gave you is one-to-one. Because if it's not one-to-one, they don't want you to find the inverse. And so you might want to make a note there. That means you want no even exponents, no absolute values. No even exponents. No absolute value. So you can just look and tell very quickly, just convince yourself the way I did. I just did it by habit a moment ago when we were doing that number 10. I made the remark, I didn't write anything down, but I said, yeah, I can convince myself very quickly that they're one-to-one. Now, if that had been an x squared minus 7, we would have had trouble. It wouldn't have been one-to-one. But there are no even exponents, no absolute values. Yeah, that looks like it would be one-to-one to me. Once you've convinced yourself that the function is one-to-one, tell me in words, what does an inverse do? Think back to the first inverse we found. We were looking at those ordered pairs. What does an inverse do? Loosely speaking, an inverse, I think I even wrote it out some for you. An inverse does what? Swaps x and y. Okay, so you're looking at your equation. I'm going to say swap x and y. Everywhere you have an x, write a y. Everywhere you have a y, you write an x. The equation you have at this point is a form of the inverse, but it's not written as a function. So the next step, solve for the new y, solve for y, and now whatever you have, once you do step 3, you'll have y equals, you have y on one side, you have something else on the other side. The something else is the answer. The fourth step, and my lab will do this fourth step for you. They're going to replace y with f inverse of x. You're replacing the y with the inverse function notation, but my lab will type out f inverse of x equals. All you have to do is type in whatever you found once you solve for y. You'll see what I mean in a moment. Any questions there? You all written that down? Number 11. Whole point of everything we've been doing. How do you find the inverse when you're given a one-to-one function? Determine whether the function is one-to-one. If it is, find a formula for its inverse. Now, if it's not one-to-one, all we have to do is click not one-to-one and we're through with the problem. So let me write this down. This is number 11. They give us the function f of x is equal to 7 over x plus 5. So first thing they want to know, is this one-to-one? You don't have to show any work to prove or disprove that it's one-to-one. It's what do you think? Is it one-to-one? Think about what I said. Is this function one-to-one? Yes, there are no even exponents. It's just the x to the first power. There are no absolute values. So yes, we can say this is one-to-one. I guess it'd be better if it hadn't been one-to-one, because then we wouldn't have any more work to the problem. But as it is, yes, it is one-to-one. Now they want us to find the inverse. And notice how they've written it. They've already typed in the f superscript -1 of x. They've already typed in that function notation. That's why I said it's really just a 3-step process. Once you solve for y, whatever you have on the other side, that's the inverse. That's the thing you're going to type in. So let's apply our little recipe to find the inverse of this function. We verified that it's one-to-one. Now we want to swap x and y. Wait a minute, I don't even see a y here. Look at this, there's not even a y appearing. What's acting like y? Something there is just a fancy way of saying y. F of x is just a fancy way of saying y. So think of that as a y. So y becomes x. X becomes y. The function notation is just a fancy way of saying y. So y became x. X became y. We did the second step. The third step solved for y. Well, I think I'll think of this x as an x over 1. Does that give you a hint about what I'm about to do? I need to get y by itself. I need y by itself on one side of the equation. What do you think I'm going to do? I got to get that y out of the denominator. What do you think I'll do? Okay, I could do that. I was going to cross multiply. A fraction equals a fraction. You can go x times y plus 5. X times y plus 5 is equal to 7 times 1 is just 7. If you multiplied by that denominator, y plus 1, the way Paris said, you put, not y plus 1, y plus 5. You put the y plus 5 here, it cancels, you have the 7. You put the y plus 5 here, you get the exact same thing. I don't know why I prefer cross multiplying. It gives the exact same thing. I need to get y by itself. I think I'll distribute through the x. Distributing through the x on the left side, we have x times y is xy plus, what are we going to have? What else are we going to have here? 5x, I agree, equals 7. You need the y term by itself. There's only one sensible next step. You're trying to get y by itself. What should we do? Okay, so we're going to move that over, and that's going to become a minus 5x. I agree. So we have a 7 minus 5x. We have one additional step. X times y. What are we going to do to undo that multiplication? Divide. to give us y equals 7 minus 5x all over x. And as I said, that's really the thing on the other side. That's your answer. There it is. That's the inverse. That's what they want you to type in. Now this fourth step, replace y with f inverse of x. But as I said, when you're doing the homework, as soon as you get y by itself, the stuff on the other side is what you're going to type in. Any questions there? So we come over here. I'll type in my fraction hot button, and on top I have 7 minus 5x, and on the bottom I have just an x. Any questions there? The f of x is just a fancy way of saying y. So when you start swapping the variables, that y became x, the x became y. Any questions? Okay. Let's do another one. Number 12. Determine whether the function is 1 to 1. If it is, find a formula for its inverse. This is number 12. F of x is equal to x cubed minus 7. Well, what do y'all think? Is that 1 to 1? Yes, I see an exponent though. I see an exponent and it's still 1 to 1. It's odd, that's right. An odd exponent is fine. There's no x squares, no x to the fourths. So yes, this is 1 to 1. And once again, if it isn't 1 to 1, then you're through with the problem. So I don't think there'll be any like that in the homework, okay? We're going to make you go through and actually find the inverse. Here goes, okay. Okay. We want to swap. Remember the little sequence of steps. Verify it's 1 to 1. I didn't write that down. Is 1 to 1. Swap x and y. Once again, I don't see a y. What's acting like y? F of x, that's my y. So my y becomes an x. My x becomes a y. We need to get y by itself. What do you think I'm going to do first? We're trying to get y by itself. Add 7, I agree. So we're going to have an x plus 7 equals a y cubed. Uh-oh, we need to get rid of that cube. What can we do? What undoes a cube? A cube root. Realize we were using that notation of a radical getting rid of an exponent back at the beginning of the semester. Now we're seeing that those things are inverses. That's why the radical will undo that exponent. When they're performed consecutively, they cancel each other out. So that cube root of y cubed becomes just a y. And what have we got on the other side? A cube root of x plus 7. There's the inverse. That's the thing I have to type in. All these concepts that we've used all semester, very early on we started, radical will get rid of an exponent. Well, because the radical is the inverse of that power function. Any questions before I type it in? Let's see. I go to the cube root, the nth root hot button, and up here in that little index, I type in my 3, and underneath the radical, I type in x plus 7. Any questions there? And I think number 13. Oh, it's complete in the square. Those circle problems are never going to go away. And a cut point problem. Look at that. We're through with the new. Oh, another cut point problem. We're through with the new material. Any questions there? I'm trying to think. Normally this lesson takes an hour 15 minutes, and this video is only an hour 5 minutes. Is there something we didn't do? Did I skip something? Let me look again. What? No, we did them all. I guess the way I was just being lazy talking y'all through on things like number 4, not writing the stuff down. That must be what sped us up, okay? Yeah, but I would have paused that the other time as well for the other classes. I don't want to say the stuff. I don't want to say anything that could be, I'm gonna stop the recording.